Welcome to Next Gen Manufacturing Nexus. Today, we're diving into something called CNC machine validation. Now, this isn't just about boring technical specs. We're talking about the invisible process, the one that makes sure a surgical implant is perfectly safe every single time. It's really the journey from a line of code to, well, a life-saving cure.
Okay, so check this out. At the absolute heart of modern manufacturing, you've got CNC machines just like this one. These things can sculpt the toughest metals. We're talking about carving steel into these incredibly intricate, life-saving parts with microscopic accuracy. It's just engineering at its absolute peak, right? But, and this is the big question, is being precise the same thing as being safe? When someone's life is on the line, is just being accurate enough? Look, making one perfect part, that's one thing. But how do you prove your machine is going to crank out 1,000,000 perfect parts without a single flaw every single time? Now that's the real challenge.
And believe me, the stakes are unbelievably high. Get this, the FDA says that 7.7%, that's almost 1 out of every 12 medical device recalls, are because of software failures. Think about that. It's not the metal or the machine breaking, it's the code, the digital instructions telling the machine what to do. That's where things can go critically wrong.
So this brings us to what we call the precision problem. Because in the world of medical manufacturing, there is absolutely no such thing as close enough. An error you can only measure in microns, that can be the difference between a successful surgery and a total disaster. There is literally zero room for error.
And listen, this isn't just some theory we're talking about. The regulators are watching. This quote from an industry forum, it's a perfect example. The FDA is literally sending out warning letters to companies for this exact thing, failing to validate their CNC processes. The message couldn't be clearer. You have to do this. It's not optional.
Okay, so here's why this matters so much. If you can't prove your process is reliable, the regulators can force you to inspect every single part. That's called 100% inspection, and it is a logistical nightmare. It's painfully slow, it's insanely expensive, and for some parts, it's just plain impossible.
So how do you avoid that nightmare scenario? Well, it all comes down to understanding two words that get mixed up all the time: validation and verification. They sound similar, right? But knowing the difference is absolutely key to building a process you can trust.
All right, let's start with verification. Verification is all about the finished product. It's pretty straightforward. It's asking the question, did we make this part correctly? You pick up the finished piece, you measure it, you check it against the blueprint. Did we hit the specs? Yes or no. It's a simple check of the final result. Validation, though, that's a whole different ballgame. It's not about the part, it's about the process. It asks a much bigger question. Are we using a process that can always make the part correctly? Think about sealing a sterile medical package. You can't test the seal without opening it, right? Which ruins the product. So instead, you have to validate the sealing process itself to know it works every time.
So let's put it simply. Verification is reactive. It's looking backward at what you just made. Validation is proactive. It's proving you're going to make it right from the very beginning. You really need both, but it's that validated process that's your ticket out of that dreaded 100% inspection trap.
Okay, so how do you actually do this? How do you validate a process? Well, the industry has a rock-solid 3-stage framework for it. It's known as IQ, OQ, and PQ. And each step builds on the last one to create a totally bulletproof system. So the steps are installation qualification, or IQ, then operational qualification, OQ, and finally performance qualification, PQ. And you have to do them in that exact order. It's a logical progression that builds confidence at every stage. First up, IQ, installation qualification. This is basically the did we plug it in right check, but way more intense. You're making sure the machine, all the power, the air supply, the safety guards, everything is installed exactly the way the manufacturer said it should be. It's the foundation for everything else.
Next up is OQ, or operational qualification. Now you're testing what the machine can actually do. You push it to its limits. We're talking highest speeds, slowest feeds, the whole 9 yards. It's like finding the red line on a car. You're defining the worst-case scenarios to find the perfect, safe operating window that guarantees a good part every time.
And finally, there's PQ, performance qualification. This is the final exam.
This is the real deal. You run the machine just like you would on a normal day, with the actual materials, the real operators, and you do it over and over again for long runs. You're proving that the process doesn't just work on paper, it works day in, day out in the real world.
All right, so that IQ, OQ, PQ framework, that's the gold standard. But technology never stands still. It's pushing us towards something even smarter, even more proactive. What if you could validate the whole process before you even touch a single piece of metal?
And this is where the digital twin comes into play. It's amazing. Using software like NC Simul, you can create a perfect digital copy of your entire machine setup. Think of it like a flight simulator, but for manufacturing. You run the real G-code, you simulate the whole process, and you can spot any potential crashes or errors in the virtual world. You're basically de-risking the entire job before you've spent a dime on material.
Okay, so validating in a virtual world is a huge step up. But what's next? What if the machine could validate itself? Not just one time, but constantly, in real time, while it's actually running. Yeah, that's the next frontier.
So here's a classic problem everyone in machining faces. Cutting tools get dull. They wear out. And as they wear out, the quality of your parts starts to suffer. So the big question is, how can you predict when a tool is about to fail without having to stop the machine all the time to check it? The answer lies in monitoring something called flank wear. You can see it in this image here. It's that tiny bit of erosion right on the cutting edge of the tool. That little patch of wear is the best clue you have that a tool is on its last legs and is about to start making bad parts.
Okay, now for the really cool part, the breakthrough. Some amazing research has found a direct link between that tool wear and the machine's spindle load. That's a signal the machine is already tracking, so you don't need to add any fancy, expensive sensors. The machine can literally use its own data to check its own health. It's simple, really. As the tool gets dull, it works harder, and the spindle load climbs in a really predictable way.
And that is a total game changer. It means you can build an automated, sensor-free system that knows exactly when a tool needs to be replaced to maintain quality. We're moving away from that old model of validating a process once to a new world of dynamic, real-time quality control that's always on. So this really leaves us with a huge shift in how we think about all this. As our machines get smarter, the question isn't just how do we validate a process? The new question is, how do we build processes that don't just get validated once, but actually stay validated every single second they're running? Because the future isn't just about making things right, it's about creating systems that literally can't get it wrong.